Hi guys. So what we're going to look at today is a really cool application of systems of inequalities. Now what we're going to do today, it really is just one additional step, two additional steps for what we've been doing with our word problems for systems of inequalities. But what it allows us to do is to take that solution that we can graph and actually find either maximum or minimum values if we're given more information. So what we're going to do to start is just look at an example where it's not the word problem, but you can just see the process. So what's going to be new whenever we do this, in addition to our system of inequalities, we're going to have what's called an objective function, which is going to be something that looks like this. Now that objective function is something you do not graph that, okay? That does not get graphed. That is just used basically on our last steps. So it's not something that we graph, but it's something that's going to help us answer our question. And when we get to the word problem, you'll see that a little clearer. But we're just going to look at the process right now. So the first thing we're going to do is really just review how to graph a system of inequalities. So I'll start by graphing x is greater than or equal to 0. Well, that's going to be everything to the right of this line. Y is greater than or equal to 0, everything above this line. And then x plus y is less than or equal to 6. Well, let's solve for y. Y is less than or equal to negative x plus 6. So that's going to be a y-intercept of 6 and a slope of 1, or negative 1. Solid line because it's or equal to, and because it's less than, I'm going to shade below. So the area that's below the diagonal, to the right of the vertical, and above the horizontal is that little yellow triangle right there. And what we just did is nothing different than we've done last class. The next part is the new steps. So what we're going to do is we're going to evaluate kind of our maximum or minimum values of this region based off of this objective function. So all you need to do first is find the vertices of your shaded region. Well, this one has 3 vertices. There's one here, here, and here. So I'm going to list those coordinates. I've got 0, 0, 0, 6, and 6, 0. Well, using those vertices, I'm going to plug those vertices into this objective function to come up with the possible maximum and minimum values. So what I'll do is I'll just take that 4x plus 5y and plug in 0, 0. Well, 4 times 0, 0, 5 times 0, 0, that gives me 0. Now let's try it for 0, 6. 4 times 0 plus 5 times 6 is 30. And then the last one, 4 times 6 plus 5 times 0 is 24. Well, what we can do now is look at those C values that those vertices gave us. Those are the possible highest or lowest values on this shaded region for this objective function. Now, depending on the problem that you have is which one you'll want to use. In this case, we're just going to list both just to get used to it. So the minimum value of C is 0. That happens when x is 0 and y is 0. The maximum value of C is 30, and that occurs when x is 4 and y is 6. So what this does, again, it allows us to be able to evaluate that function for this whole system, that whole shaded region, and find the highest or lowest point in that whole region for this equation. Now let's look at a whole problem so you can kind of see where this equation comes into place. All right, so it's a long problem here, but bear with me as we get through this. Well, a lot of this is really the same thing that we've been doing with systems of inequalities. The two additional steps is to find the objective function and then plug in those vertices to find those min and max values. So let's go ahead and read through this. So school is looking at ways to get their faculty for their new school. They're going to hire teachers and teacher aides. The amount of money that they're going to spend on their salaries depends on how many they hire. Okay, so the average teacher salary is $30,000. The average aide salary is $20,000. Then the board has a lot of criteria. Okay, so the building cannot have more than 50 members. They have to have at least 20 members. They have to have at least 12 teachers. And then there's a certain teacher to aide ratio that they have to meet as well. So now what we're going to look at is the actual question. The actual question here is to determine the number of teachers and aides that would represent the minimum cost to the school district. Our objective function is going to be what answers that question. So the first thing we're going to do, just like we do with normal systems word problems, is define our variables. The 2 variables here, we'll call them x and y. We've got the number of teachers and the number of teachers' aides. So our objective function is going to be based off of what answers the question and our variables. We're trying to find the minimum cost to the district. Well, what actually costs money are the salaries. Teacher salary is $30,000, aide salary is $20,000. So this objective function is going to be, what's that cost? Well, that's going to be $30,000 times the number of teachers plus 20,000 times the number of aides. And again, we are not graphing that. We are just using that for when we get to this kind of last step to answer our final question. So now we're going to write our constraints. This is nothing different than we did last class with our word problems. We're going to use basically all of this information to write a system of inequalities. All right, so let's go ahead and come up with those. The building cannot have more than 50 faculty members. Well, faculty members are composed of teachers and aides, so the teachers and aides have to be less than or equal to 50. The school has to have a minimum of 20 faculty members, so x plus y has to be at least 20. There has to be at least 12 teachers, so x has to be greater than or equal to 12. And this is kind of the hard one to write. It says the number of teachers must be at least half the number of aides. So the number of teachers must be at least, so greater than or equal to, half the number of aides, which is y. All right, so what we'll do now is we'll actually graph this region. So in order to graph this, let's go ahead and solve for y in each of these equations. And let me scoot this one over a little bit. All right, so in this first one, in order to solve for y, just subtract. So y is less than or equal to negative x plus 50. Now I gotta change my scale on this graph a little bit. I'll just make it go by fives. So we'll say 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. And we'll have to do the same thing on the x-axis in order to keep this, in order to keep our scale for our slope. So we'll make this as well. This is 5, 10, etc. All right, my other equation, we'll go ahead and solve for y. So y is greater than or equal to negative x plus 20. So y-intercept of 20, slope of negative 1. All right, x is greater than or equal to 12. So we'll go ahead and graph that. It's not going to be right on the line, but again, we're just kind of estimating or graphing up as close as we can get to that region. And then this last one, x is greater than or equal to 1/2 y. To solve for y, I would multiply by 2, so 2x is greater than or equal to y. Kind of easier to see though if I write that as y is less than or equal to 2x. So from 0, 0, I'm going up 2 and over 1. And there's my graph. Now there's one other constraint that we do need to consider that's going to kind of help make our picture. This is one you're going to see frequently in these word problems. We have to have at least 12 teachers. There's no minimum on the number of aides listed in the problem, but we know we can't have a negative number of aides. So I also need to include that y is greater than or equal to 0. All right, so now we got to find basically that shaded region. So I want to shade below the blue line. I want to shade above the green line. I want to shade below the red line and to the right of the purple line and above that black line as well. So that is my shaded region. So what that region is, that region represents all the possible combinations of teachers and aides that would fit that criteria. And that's the same thing that we did last class. What we want to do now, though, specifically is find, hey, what's going to be the lowest cost for the district? This is where the vertices come in. So those vertices are the potential min or max values of this region. So what we need to do is find what all these vertices are. So I've got 1, 2, 3, 4, 5 of them in this picture. All right, so the first one down here, I'll go ahead and write the easy ones first. That green, where the green line meets the black line, that vertice, I'll list them over here. That one is 20, 0. We've got 50, 0 over here. And then we've got some that are kind of hard to see on our graph. So what we actually need to do is actually find the intersection of those points. So we can either do that algebraically. If you want to do that in a calculator, that's okay. What you would do if you're doing this in a calculator is you could just graph those lines and find intersect on your calculator. Now, if you don't want to do it that way, you want to do it algebraically, I do want to review that. So we'll go through that algebra real quick. So the first intersection I'm looking for is where the purple and the green meet up. So the purple line is x equals 12. The green line is y equals negative x plus 20. So if I want to find that intersection, I want to know when y equals negative x plus 20 intersects when x equals 12. So I'm going to plug in 12 for x, and I get that y equals 8. So that intersection point right there, when x is 12, y is 8. All right, well, now let's find the intersection of the purple and the red. Again, we know that x is 12. So to find where that intersects, I'm going to plug in 12 for x, and I get 24. So 12, 24 is the intersection of the red and the purple. And then the last intersection point is the hardest one algebraically, but we'll go ahead and find it. So where the red and the blue made up, again, if you want to do this in a calculator, you can just graph y equals negative x plus 50 and y equals 2x, and you can just graph those and find the intersection on your Casio, G-solve intersect. But if we want to do it algebraically, I'm just going to set those two equations equal. I want to know when y equals 2x is equal to y equals negative x plus 50. Well, 3x equals 50 over 3. 3x equals 50 divided by 3. X equals 50 over 3. To find the y coordinate, take x, plug it back into either function. So 2 times 50 over 3 is 100 over 3. So those are my intersections, or my vertices. Those are the possible min and max values for this problem. So now I'm going to plug those x and y's into that objective function. So for the first one, I'll just show it over here because there's a little bit more space. I would plug in. So if I plug in 20 for x and 0 for y into that objective function, then I'm going to end up with a c value for that one of 600,000, sorry. If I plug in x is 50 and y is 0 into the objective function, I would do 30,000 times 50 plus 20,000 times 0, and that's going to give me 1,500,000. If I plug in x is 12 and y is 8 into that objective function, then I'm going to end up with 520,000. If I plug in 12 and 24, again, same thing, just plugging them into that same original function, then that's going to give me 840,000. And then this final one, if I were to plug in those values, that 50 over 3 and that 100 over 3, now those aren't the actual numbers I could use because we're not going to have a fraction of a teacher, but that would give me 1,166,667. So now that we're looking at those values, we're going to actually answer our question. So if you remember, the original question wanted to know what the minimum cost to the district is going to be. Well, if I want to know the maximum cost, that would be my answer. But since we're looking for the minimum cost to the district, what we're looking for is which C value ended up the lowest. And that would be this C value here. So the lowest cost to the district would be $520,000. How they're going to get that is when you have 12 teachers and 8 teachers' aides. And then, again, if you want to know what that amount was, that would be the $520,000. All right, so let's do the same process, just with a different example. If you feel comfortable with this, you might want to try this one on your own, at least in little parts of it. So try to figure out your variables, your objective function, your constraints. You can pop back in and check to see if you got them right. All right, so on this first one, Judah is making pies and cakes, a profit of $15 in each pie, a profit of $12 on each cake. So he can sell, he needs to have 15 minutes of work and 2 cups of sugar for the pies. He needs 10 minutes of work and 3 cups of sugar for the cakes. He has 24 cups of sugar and he has 2 hours to work. And then some additional information, it says with our demand, then he has to have at least twice as many pies as cakes. So what we need to do is determine, first of all, what our variables are in order to answer our question. So we want to know how many of each type he needs to make in order to make a profit. Well, the two things that are our two variables are going to be the number of pies and the number of cakes. Our objective function is going to be what answers the question. How many of each type should he make to maximize his profits? So his profit is $15 for each pie and $12 for each cake. So there's our objective function. Our constraints are going to be what answers all the questions. So some of these are a little bit easier than others. The first one we need to look at is basically a work constraint. All right, so what we know, he needs 15 minutes of work for every pie. He needs 10 minutes of work for every cake. And he only has 2 hours, or 120 minutes. So that means if every pie is 15 minutes of work, 15x is the total number of minutes he'll spend on pies. If every cake is 10 minutes of work, 10 times y is the total number of minutes he'll spend on cakes. He only has 120 minutes to spend. So that's our constraint. And we'll solve for y and graph it here in a little bit, but let's just write our constraints first. All right, the second constraint he has is a sugar constraint. So let's look at this one. He needs 2 cups of sugar for every pie. He needs 3 cups of sugar for every cake. And he only has 24 cups of sugar left. So we'll write that constraint based on that sugar. It's going to look very similar to the one we just did. Every pie is 2 cups. Every cake is 3 cups. And then since he only has 24 cups of sugar, that has to be less than or equal to 24. So that's our sugar constraint. All right, the other information that we know, he has to have at least twice as many pies as cakes. Now this one can be pretty tricky to write. So what we know first of all to start with, he has to have more pies than cakes. So x has to be greater than or equal to y. All right, so at least we know that. Now twice as many means the number of cakes that we have has to get multiplied by 2. So that means now x is greater than or equal to 2y because the number of pies is going to be greater than or equal to twice the number of cakes. So twice as many pies as cakes. That one can be probably one of the harder ones to write. All right, and then our last one, he has to make a minimum of 2 pies for a pre-order. So that one's probably the easiest one to write. So if he has to have a minimum of 2 pies, then that means that pies has to be greater than or equal to 2. All right, so before we graph this, let's go ahead and solve for y and those other equations. So on this first one, we'll rewrite that. 10y is less than or equal to negative 15x plus 120 divided by 10. That's going to be negative 3 over 2x plus 12. So we'll go ahead and graph that one. So y-intercept of 12, slope of negative 3 over 2. And I miscounted there a little bit. Let me fix that. That's a little bit better. There we go. All right, so there's the first one. All right, the next one again, we'll go ahead and solve for y there. So I'll do that one over here. So 3y is less than or equal to negative 2x plus 24 divided by 3. So y is less than or equal to a negative 2/3 x plus 8. All right, we'll graph our x is greater than or equal to 2y. So I'll just rewrite that as 2y is less than or equal to x, which then divide by 2. So y is less than 1/2 x. So we'll go ahead and graph that one. All right, and then my last equation, x is greater than or equal to 2. And if you don't see it, there's one more constraint that we do want to include because we can't have a negative number of any of these. I'm also going to include that y is greater than or equal to 0. All right, so in this big mess of lines, I got to find where my actual shaded part is. So we're going to start with this blue one. I'm shading below the blue line. I'm shading below the purple line. I'm shading below the pink line. And I'm shading to the right of the red line. So below all three. And then the right of the red is this little triangle in here. So this one's a pretty messy picture with all those lines, but it's really easy to find the vertices, at least on this one. So this one we've got 1, 2, 3, 4 vertices, and they're all nice, easy integers to see. So that first one is 2, 0, 2, 1, 6, 3, and then 8, 0. So there's our vertices. So in order to find our answer, we're going to take those vertices, plug them back into the objective function, and figure out, again, to answer our question, which one is going to make the maximum profit. So I'll go ahead and put that up here. So if I did 6 and 3, so I would do 15 times 6 plus 12 times 3. Which would give me $126. All right, I can do 15 times 8 plus 12 times 0. So 15 times 8 would give me 120. 15 times 2 plus 12 times 0 would just be 30. So we definitely don't want to do that one. That's not a lot of profit. And then my last one, 2, 1. 15 times 2 plus 12 times 1. It's going to be a little bit bigger, but still pretty small. And that one's going to give us $42. So out of those numbers, you can see there are definitely two that are bigger. And that's going to be, this first one is our absolute maximum, though. So if he wants to maximize his profits, he wants X to be 6 and Y to be 3. So what that stands for, he would need to make 6 pies and 3 cakes. All right, so that is it. So just keep in mind, again, a lot of this is really similar to what we did with our systems of inequalities. It's really just a systems of inequalities word problem, and then you kind of add that extra step of find your objective function, find the vertices, and then plug those vertices into the objective function to answer the question. Other than that, it's no different than the systems word problems that you guys looked at last class.